Hi, welcome back to AP Physics C, Electricity and Magnetism. We're getting close to the end here. We only have a couple more things to address, which are inductance, RL circuits, so resistor inductor circuits, RC circuits, which are resistor capacitors, or excuse me, LC circuits, which are inductor capacitor circuits, and finally Maxwell's equations, which kind of just sums up a lot of what we've been talking about here. All right, so inductance. So an inductor is a component that stores energy temporarily in a magnetic field. Okay, what it is, it's essentially like a solenoid, right? It's made by coiling wires into many loops. But when you place it in a circuit, the inductor stops the current in the circuit from jumping to the maximum value. So it's like, I want to use it, and it's going to go up to a point, it's going to increase the magnetic flux, but it'll oppose the direction of the current. There's a lot of real world applications in it. You can see there's a picture here of a metal detector for inductors. So there's like a really interesting things. So a lot of when you tune radios and so forth, like they actually use inductors because it wants to bounce back the signal, and we'll get more into that when we talk about the different types of circuits. So inductance itself is a property of the inductor, and it's essentially the ratio of magnetic flux to current flow. So simple enough, L is equal to magnetic flux. Let me write that a little bit bigger. So magnetic flux, so B to current flow. Okay, so simple enough. I mean, you can do some simple calculations there to determine the magnetic flux. You can determine the I. You can also say, hey, magnetic flux is B times A. So it allows you to just substitute in a different, many different formulas to simplify that to get what you're looking for. Now, the circuit itself will produce a change in magnetic flux, thus induces an EMF due to its own current, and we call this self-inductance. And the EMF that is created is equal to negative L di dt. Right? And so what's happening, you're changing current with respect to time, and you multiply that by the inductance, and that'll allow you to figure out the EMF that is induced. I did forget to mention inductors are measured in henries, which is a capital H. But again, you're going to see nanohenries, microhenries, picohenries, femtohenries, right? So there's going to be like different things that you could have to convert really, because you got to get back to henries. And then you're also energy, right? So energy will be stored in these inductors due to the magnetic field. And it's just simply U equals 1/2 Li squared. So the energy stored is 1/2 times the inductance, right, times current squared. So let's just do a simple calculation here with, it's a solenoid, right? So sometimes we may not have addressed a lot with solenoids. So just to make you aware of it, the magnetic field in a solenoid is simply mu naught Ni, right? Where N is not the number of turns. That is called turn density. So it's number of turns per unit length. Okay. And so part A says find the inductance of the solenoid. So this is like a deriving expression question. So we're going to use that. We know that phi, right, magnetic inductance is going to be BA. Well, here's my B, and I'm going to substitute in the N over L. So I'm going to get mu naught N I A over L. Okay, so that's the amount of magnetic inductance that this solenoid would have. And then what we do is we simply keep substituting in. So now we have inductance, and this L down here, and I'll make it a lowercase l, that is the length of the wire, right, where the capital L is the inductance. I apologize, I keep forgetting about that. So we have N times magnetic flux over, excuse me, I wrote the L again. This is not L, this is I, so this is the current. So now I'm going to take this and plug it into that part of the equation. And so we get an inductance of N, number of turns, times mu naught Ni A divided by the length of the wire divided by I, right? So now we just simplify. N times N is N squared. This I cancels that I. And so we end up with mu naught N squared A over L. So this is how you calculate the inductance on a solenoid. So now what we want to do is part B is now actually doing the calculation. So we derive the expression. Now we need to calculate the actual inductance of a solenoid. So we're going to use our formula that we just calculated or just determined. So mu naught 4 pi times 10 to the negative 7th tells us that it's 300 turns. It has a cross-sectional area of 4 centimeters, but we need to turn that into, and that 300 is going to be squared. We need to turn that into square meters. So we're going to divide that number by 100 squared. And then we're going to divide this by our, tells us the length of the wire, the length of the solenoid, 25 centimeters. Convert that to meters, 0.25. And so we get an inductance of 1.81 times 10 to the negative 4th henries, or you can call it 18.1 microhenries. Sometimes they may tell you reported answer in microhenries, but either one of those will be correct. 18.1 microhenries or 1.81 times 10 to the negative 4th henries. All right. Part C says calculate the self-induced EMF of the solenoid if the current it carries decreases at the rate of 50 amps per second. So the induced EMF, right, in the inductor is going to be given by negative L di dt, right? That's our self-inductance equation. So we're going to do negative L, so 1.81 times 10 to the negative 4th. Now they tell us, they actually give us the di dt. We don't have to really do anything in calculation, but you do have to be careful because it says it decreases. So that's going to be negative 50 amps per second. And you just multiply those two, right? So you end up with 9.00 times 10 to the negative 3 volts. Okay, so in this video, again, just to recap a little bit, we did talk about inductance, right? Where we talked about inductors, what are inductors? We're given equations for inductors. We're given an equation for self-inductance. Okay, and then in our example problem here, we just really did a very special or specific type of inductor, which is a solenoid. So in the next video, we're going to look at resistor inductor circuits, which is just going to be another circuit added into the ones we've already talked about in this course. So I hope to see you there.